All right. Let's see here. Not sure what to do. Participants. Jesus. Of course, the first question would be, can I see your baby? That's really strange. Good morning, good morning. Oh, it's the afternoon? Is it? Oh, it is noon, yeah. Let's see here. Hello, people. All right, I am doing this only because combo circuits are really hard. So, if you have any questions, let me know. Can you hear me, first off? I've never done this before. Wonder Wednesday? I have done no preparation for that yet. Can we see your baby? He's asleep, so no. Now, if you don't have any questions about combo circuits, I'm fine with that. Please. Morgan, no. He's asleep. Julianne actually has a question about circuits. Crazy. Okay, yeah, that question was kind of tough. Why are parallel circuits used in household circuitry? One of the main differences between a parallel circuit and a series circuit is that a parallel circuit has direct access to the battery, right? Every component in a parallel circuit pulls power directly from the battery of the circuit. So if you break or you turn off a switch in one branch of a parallel circuit, all the other branches still have power, which is important. You don't want to turn the light off in your living room and then turn off all the electricity in your house. A series circuit, if you break the circuit at any point, there's no longer current flowing through the circuit. So in household electronics, we use parallel circuits primarily. So you turn off the light switch, and only that one circuit could shut off, not the whole thing. All right, you're welcome, Julianne. What I wanted to do is I wanted to go over the one combo circuit packet question, the number one from the very back. I'm not sure where you guys are at. Is everyone done with the packet yet, or where are you guys right now? Scroll down. Do you have to make the boxes? No, you don't. But they're incredibly helpful, and they do count as your answer. So, like, the boxes are really helpful because they kind of outline every voltage drop, every current, every resistance of every component in the circuit. So it's a really good way to organize all your data. I want to try and go through a practice one really quick here, okay? Now, I know I have like some screen sharing something, and I can go my Weezer shirt. Sure. There you go. All right, Zach. I hope you got it. Okay, now, what was I saying? Right. The VERP boxes, I call them: voltage, current, resistance, and power. So if we have two, I'm just writing on some paper here. I'll show you in a second. Too bad, Zach. Okay. So if we have a parallel circuit like this, so we have a battery and 3 resistors. Let's just say, for simplicity's sake, the battery is 9 volts. The resistors are each 5 ohms. Okay? They're each 5 ohms. The way we have to do the voltage, the VERP boxes, I call them: voltage, current, resistance, power boxes, is you make a row for each component and then a final row for the total. Let me draw that out here. If you guys want to follow along, you can in your notes. That'd be good. So it should look something like this. Oh, also, I'm not really familiar with this. Can you pause it and like go backwards and forwards, or no? Okay, cool. So I can flash this up here and then keep going. Oh, wait, no? Okay. Julianne said yes, and Zach says no. No, sir. It's on the back of the focus, Zach. Focus. Okay. So we have a 9-volt battery hooked up with 3 5-ohm resistors. The first thing you do is you make your chart and you plug in everything you know. So we know that each of these are going to be 5. You can't see that. Okay. 5 down the row, and we know the voltage is 9 volts. So we fill it out like this. Okay, now on my screen, it's flipped backwards. Is that the same for you? I hope not. Thanks. All right. Okay, so we have this here. Now, it might be kind of instinctual to say, okay, the total resistance, you just add them up. Like in a series circuit, you just add them up and the total resistance would be 15. However, this is a parallel circuit. So when you add more resistors, you actually decrease the total resistance, which is a little backwards when you think about it. With series, you add more resistors, the resistance increases, and that makes sense. My analogy for parallel circuits is like if you're on a crowded highway and you open up a new lane, suddenly the traffic overall goes down. So the resistance goes down when you add a new component in parallel. Okay. And so there's a kind of a weird equation you use to calculate the total resistance. It's on your equation sheet. And it looks like this: 1 over RT equals 1 over R1 plus 1 over R2 plus 1 over R3. All right. Like that. And so you do 1 over 5 plus 1 over 5 plus 1 over 5. All right. And so you end up with 3/5. But that's not your answer. That's not the total resistance. You have to then invert that to get 5/3, and that is your total resistance. Okay. So that gets us a total resistance of 5/3, which is a number equal to 1.66. All right. Now, I know this all seems really complicated, but really, at heart, this is just Ohm's law. That's it. It's just a Ohm's law in box format. So we take V equals IR, and we now can get total current. We can get the current for each individual one. Oh, the one big thing is, what is the main rule? Somebody type in the Google Doc. Tell me, what is the main rule for parallel circuits and their voltage? What do we know about that? Yeah, it stays constant. Good job, Cop. So, and Zach, you too. You're good too. All right. So what we can do is we can take that 9 voltage and just roll it all the way up through the top. So we get 9, 9, 9, and now it's just Ohm's law all the way through. And then for power, I think the equation's on your equation sheet. I could be wrong, but it's power is current times voltage, P equals IV. You can just go all the way through that way. All right. It's Wednesday, right? Yeah, okay. So you don't have doubles. All right, so we can just do a quick combo one. I only have 7 people watching. Yeah, that's okay. Let's do, if you want to just flip over to that last. Oh, excellent. Great. Cool. Oh, excellent. This is kind of neat. If you want to flip over to the last page there, look at the first combo circuit one, okay? Let's see. I'm trying to remember what that was. Yeah, I can pull it up. I have it on my computer. Okay, so the first one there has, right. So it has a battery hooked up to 4 resistors. Now, obviously, not every circuit is going to be a super simple, all parallel or all series circuit, right? There are going to be many different types. And they can be really complicated, and I hate them. So what we're going to do instead is we're going to redraw this and bring it down into a simple circuit. You're not supposed to be able to do these super big complicated ones on their own. You're supposed to turn them into simple ones, right? So you have one that looks like this here. Okay. It should look like this, right? Now, it may not be immediately apparent how to simplify this circuit, but what you can do is you can collapse that parallel resistor, and then what you have is a just a series circuit. So there are no directly hard and fast rules, and that's why on the Edpuzzle, which I know everyone did, right? The guy was kind of being a little weird about it. He's like, you just have to be one with the circuit and really look over the circuit and understand how you can simplify it. But that's not good enough. So what I like to think of is you can only collapse and only squish together resistors when there is only one resistor per branch. Now, how do you figure out what a branch is you look at what are called nodes. Not with waves. I know the vocab's confusing. We're not talking about standing waves. But here, these nodes are where 3 or more wires come together. So if you go from one node and you follow the wire and the components back to the other node where they return, if there's only one component on that branch, you can then squish it together with another branch that only has one component. So here, there's only one resistor on each branch. So you can squish that together, and what you're left with now is a very simple series circuit with just 3 resistors. That's why the worksheets in the packet kind of use the phrase equivalent resistance, because you're trying to find what is one resistor that I can make that's equivalent to R2 and R3. And so what I do is I refer to that as R23. Now, again, that's not everyone doesn't do that. That's just how I do it. Helps my weird brain think that through. So we end up with now just a regular old series circuit. So what that means is that this circuit is different than all the other circuits we've done, which only require 1 box. This circuit requires 2. One for the easy series circuit, and then another box to combine the 2 parallel resistors into R23. So we end up with this right here. The first box right here, and the second box. Okay. Trying to do this quick so I don't have, it doesn't look very pretty, but that's okay. Also, I'm running on like 3 hours of sleep in the past 48 hours, so it's not going to be the best. Hold on. Okay. So we have the first box here to combine R2 and R3 into R23. And we have VIRP. Over here, though, we have the final box. This final box is R1, R23, R4, and then total, right? Notice that I forgot to put a row down there. That is accidental. There we go. Now, this is labeled total, and that's kind of important because a common mistake I see a lot of people do is they put the voltage, the total voltage for the whole circuit in this box right here, the R23. The thing is that there is a voltage drop across every component in this circuit. And so the voltage across R2 and R3 is going to be different than the voltage across R4 and R1, and certainly it's going to be different than the overall. Because you know that for a series circuit, right, the drop over R1 plus the drop over R23 plus the drop over R4 must total up to the total voltage, which I believe was 15 volts, all right? And so that means that V1 plus V23 plus V4 equals 15. But down here, V23 does not necessarily equal 15. All right. So what we have to do is we're going to start off by writing down all of our givens. So we have, why do I use subscripts? Okay, no, that's a great question. Right, because what that means, okay, sorry, guys. That's a great question. When I have here, I took R2 and R3, and I don't like that this is all parallel inside of a series circuit. So what I'm trying to do is I'm trying to like clip the wires, cut out this parallel section here, and replace it with just a single resistor, which I have labeled R23. Why do I specifically use subscripts? I don't know, it's just a way that I keep track of everything, but you don't have to do it that way. Did that answer your question, Nate? Okay, cool. So let's keep going then. Let's go ahead and plug this in here. We plug in everything we know. So I'm going to start off with the total voltage as 15 volts. Again, only put down 15 volts in that total row, because that's going to be the total voltage, okay? We then can plug in all of our resistors. We know that R1 is 8. So you go over to that final box with next to our series circuit, and under R1 we put 8. We know R4 is going to be 12. We don't know what the total resistance is yet because we don't know what R23 is. So let's go over back to our R23 box here. Hold on. There we go. Okay. So we go over to our R23 box right here, and we're going to try and figure out what is the total voltage down here. So we're going to plug in 10 ohms for R2 and 40 ohms for R3. All right. 10 ohms and 40 ohms, and we're going to find out the total. Now, again, initially you might jump in, you might say, oh, that's 50, right? But instead, you got to remember that these are set up in parallel, right? R2 and R3 are in parallel. And again, the way you know that they're in parallel has nothing to do with how they're drawn, right? It's not that they are geometrically parallel. The word parallel, and those of you who've done any programming know that in programming, parallel means at the same time, like a parallel process or a parallel subcode or something like that. I don't know. Just means that two programs are running at the same time. So what that means is that if a electron goes through R2, it cannot go through R3. Therefore, they're in parallel. But like, for example, R1 and R4, we know they're in series, even though they're geometrically parallel, R1 and R4, they're not parallel together, because any electron that goes through R1 must go through R4. There's no other pathway for it to go. So we know that R2 and R3 are in parallel, All right, so what I want you guys to do here is use that equation on the back of your equation sheet to calculate total resistance, and go ahead and calculate the total resistance for R23. What would that be? Again, it's 1 over RT equals 1 over R1 plus 1 over R2. The first one who types an answer can get a Snickers or something. They should still be in my drawer on the bottom left. Oh, Kyle, you got it. Great. Okay. Anyway, so that's that. So R23 is going to be 8. All right. And so we got that. Now, again, this may be left unsatisfying because there's really nothing else we can do with this box, right? We don't know the voltage drop across R23. We don't know the current, so we really can't do anything. So right now, this little R23 box is left alone like that. But we know that this R23 row connects over to that R23 row. So we now know that we can fill out this box right here. We get 8, 8, and 12, bringing us to a total resistance of 28. And from there, we can then solve for the rest of the box, do P equals IV, V equals IR. We know that in series, current is constant. So if we do 15 divided by 28, we get 0.54. So we have this 0.54 as our total current. And since this is a series circuit, again, remember, we simplified this down to just be series. We can then say, okay, current must be constant. And we can just bring that all the way through, and then we can just do Ohm's law for that. And we finish out that box, and then the last step, like if we want to know the voltage drop across R2 or the current going through R3, all we have to do is plug in whatever we get for this row, whatever we get for this row right here, and we just plug it into this row right here, because these are essentially the equivalent row. And so then we can then just use our parallel rules to figure out all the rest of the voltage drops, et cetera, et cetera. And so we can go from there. So why don't you guys go ahead and do that? If you have any more questions, post it to Google Doc. I'll keep an eye on that. I'm going to end the stream here. I had to feed baby, so I got a bottle here. So I'm going to end the stream, and then if you have any questions, just put them on the doc. I'll be paying attention to that. Any other questions on that? Wonder Wednesday. Well, I don't know what Wonder Wednesday questions do you have about your baby? I am getting permission to put Henry on the camera. Okay, hold on.
It's a treat for those 7 kids.
Okay, and he has it on the big screen. All right, he's asleep. Okay, so there you go. Here is little Henry. There you go. All right, so. Well, okay. I'm going to end the stream. If you have any questions, let me know. Okay? He does have a lot of hair. Yes, you're right. And he's blonde. So there you go. All right. I'll be back on Monday. Test on Tuesday. You cannot tip a cow. That is a myth made up to make people run into cow fields and get attacked by cows. So don't do that. All right. Have a great one. And make sure Kyle gets his Snickers. All right. Bye.